Good morning, everyone. I'd like to get started. I'm very happy to introduce today's seminar speaker, Professor Xian Wu. She's currently assistant professor at the UT Dallas. And so Xian received bachelor's degree in atmospheric sciences from Nanjing University of Information Science and Technology, which is a formal meteorology school. And as many of you know, she came to UTIG in 2015 to work in my research group, and she graduated in 2020 in the middle of the pandemic. I couldn't properly send her off when she finished her degree, and then this is actually the first time I see her in person after she left, and it's very nice to see her back at UTIC again. So during her PhD study, she studied dynamics and the predictability of El Nino and La Nina, and specifically, she studied the multi-year predictability of El Nino La Nina duration. And her work got cited very well, and then she was awarded a competitive fellowship from the Advanced Study Program of the National Science for Atmospheric Research. And so she moved on to the next job in Boulder, Colorado. And she had a second postdoc position at the Geophysical Fluid Dynamics Laboratory of NOAA at Princeton University. And then during the postdoctoral years, she expanded her research program and then studied the decadal climate variability. And she also studied the origin of climate model bias in the tropical Pacific, which is a very long-standing problem in the climate research community. Let's see. And then she returned to Texas earlier this year to join the faculty of UT Dallas. And then she continued to expand her research program and a collaboration network. And she was already submitted proposal with Danielle at UTIG. So welcome back, and then please start your presentation.
Can you hear me well? Great. Thank you, Yuko, for the nice introduction. It feels very special to be back at UTIG and share some of my recent research since graduating. Today, I will speak about the decadal climate prediction, focusing on the tropical Pacific Ocean. I will talk about the influence of volcanic forcing and oceanic processes. It is very important to make accurate prediction or projection for weather and climate events because they can cause severe societal and economic influences. For example, in Texas, extreme events like hurricane and winter storms can cause severe damage to the infrastructure and communities. This is on the weather timescale. On seasonal timescale, Texas can suffer from drought conditions, usually associated with La Nina events. They can cause severe influence on the water resources. On long-term timescales, here I'm showing the future projection of summer heat extremes in Dallas. It is projected to increase in the future, although there is large uncertainties needs to be better quantified, which could coming from the differences in different climate models or uncertainties due to different future emission scenarios or the internal climate variability. These different timescales of weather and climate disasters calls for the importance of developing seamless Earth system predictions across from weather to centennial timescales. Climate prediction problem can be viewed as an initial value or the force boundary problem. For example, the temperature at a given location can be decomposed into three components. The first one is the one influenced by the initial states of the given system. The second is the forced response to any external forcings, and it could be also influenced by unpredictable noise. And the predictability is depending on which timescale we are looking at. At short timescales, like weather predictability, which is limited to 2 to 3 weeks because the atmosphere is chaotic and nonlinear. On seasonal to interannual timescales, we can have seasonal to interannual predictability, which comes from the land or the ocean initial conditions, which can couple with the atmosphere and extend the predictability. And as Yuko mentioned, I was focusing on this timescale during my PhD. In contrast, at longer timescales, for centennial projections, the predictability is largely coming from the external forcings, including the anthropogenic forcings, for example, greenhouse gas emissions, and also aerosol forcings. Natural forcings are also important, including the solar and volcanic forcings. There's a gap between the seasonal forecasts and centennial climate projections. Therefore, the field of decadal prediction has been growing rapidly in the last 1 or 2 decades. Decadal prediction relies on both initial condition of the climate system, but also the external forcings. In this talk, I will be focusing on decadal timescale. How do we make a climate prediction? The primary tool is the numerical Earth system model. In this talk, I will be focusing on the community Earth system model, CESM model developed at NCAR. It simulates the Earth system, including the atmosphere, ocean, land, biogeochemical, and cryosphere. All of these components are linked by a flux coupler. I'm using the 1 degree resolution, which is about 100 kilometers in the horizontal resolution, although higher resolution versions are also actively being developed. Then we will make use of the supercomputers to get the numerical answers to the physical numerical models. How do we make a prediction? Here I'm showing the setup for the decadal prediction experiment. Firstly, we can make forecast for the future by initialize the numerical model with the observed condition from today, and then run the model forward and integrate to get the answers for the future. However, we'd like to first know how reliable our model is. Therefore, we make a series of the hindcasts, which means the forecast for the past climate. The first set of the hindcasts are initialized on November 1st of 1954 for the CESM decadal prediction. Those large ensemble simulations are initialized from the observed oceanic and sea ice conditions on November 1st of this year. Then the model is integrated and run forward for 10 years to make a prediction on decadal timescales. These experiments are also forced with the CIMIP 5 historical forcings. To mimic the unpredictable weather noise, we usually run a large ensemble size. Here we have 40 members, and those ensemble spread is created by adding small perturbations to the atmospheric initial conditions. Similarly, we repeat such hindcasts for each year during 1954 to 2015. Then we could compare those long-range hindcasts with observations to understand the predictability, to estimate the predictability for observations. We could take the ensemble mean across the 40 members to estimate the predictable component. On decadal timescales, it could arise from the predictable internal variability, which is associated with the ocean initialization. It could also coming from the forced climate change. The model can estimate that based on the radiative forcings. This is the ensemble mean signal. We could also estimate the unpredictable noise by looking into the ensemble spread among the 40 members. Then we could compare the ensemble mean forecasts with observations. We usually calculate the metric called correlation scale for forecasts initialized at certain lead times and looking to how well they reproduce the past climate. Now I'm showing you the hindcast scale of the current state-of-the-art Earth system models. This is the prediction for the surface air, global surface air temperature. The lead time here is 229 average. It means we are trying to predict the past climate at a 229 year average in advance. The total correlation scale for surface temperature is pretty high almost everywhere. This is because the model can well capture the forced climate change, particularly the warming trend when the model is given the greenhouse gas emission increase. However, after we remove the effect of forced climate change, we are focusing on the internal decadal climate variability. Now, the correlation scale drops almost everywhere. This means the prediction scale arising from the initialization of the ocean states doesn't give much predictability, particularly in the tropical Pacific. This is very different from the seasonal forecasts. Like on seasonal timescales, tropical Pacific is the most predictable region due to the high ENSO predictability. However, on decadal timescales, it is not the case. This is also a concerning issue because we know that tropical Pacific is the powerful driver for global climate on decadal timescales. This will also degrade the prediction scale for the downstream effect. Therefore, we focus on understanding two questions. Is this low scale on decadal timescales in tropical Pacific arises from the intrinsic predictability limit? The nature is not predictable, or because we have deficiencies in our forecast systems, including the biases in the Earth system model or the uncertainties in the initial condition data we provide for the hindcasts. We have been exploring these questions by using the decadal prediction system conducted with CESM1, and I've introduced the setup of these experiments. In summary, this initialized decadal prediction large ensemble DPLE predict the past climate by using making using of both the initial condition in the past, but also the symmetric radiative forcings. Among the different radiative forcings, a spatial forcing is related to the aerosol forcing released by the large volcanic eruptions. And here I'm showing the time series of this aerosol forcing, which is mostly contributed by the three large tropical volcanic eruptions, Algon, El Chichen, and Pinatubo. It has been a debate that whether the volcanic information should be included in the hindcast, because for real-time forecast, the occurrence of volcanic eruption itself is not predictable. However, this volcanic information was included in the experimental setup, and it was expected to provide a source of predictability. I will show you that this is not the case for the tropical Pacific. To better isolate the influence of volcanic forcing on decadal prediction, we compare the DPLE with the parallel forecast set without historical volcanic forcing called DPLE no-volc. Then we also isolate the influence of ocean initialization by compare the DPLE, the initialized hindcasts, with the uninitialized simulations called CESM1 large ensemble. It has 40 ensemble members initialized in 1920 and run forward towards the end of the 21st century. This simulation only has the information about the radiative forcing in the past. They do not have the extra initialization information. So comparing the first and third set, we can isolate the influence of ocean initialization. Now we are looking again at the correlation, the prediction scale for the 3 CSM1 simulation or hindcast datasets. I'm focusing on the forecast scale at 1 to 10 year average. So that's the decadal time scale. And I'm also looking to the detrended surface temperature. We can focus on the internal decadal variability. You can see that the correlation scale in the DPLE with flow forcing and initialization remains low, while the prediction scale is higher in the system without volcanic forcing. When we take the difference between these two, we can find that volcanic forcing significantly decreases the correlation scale in the tropical Pacific, especially the central tropical Pacific. And we can also take the difference between DPLE and large ensemble, which shows the influence of ocean initialization. We find ocean initialization improves the prediction scale in the eastern tropical Pacific. Then we'd like to know how do those two factors influence the decadal prediction scale in the tropical Pacific. First, we are using a statistical method called empirical orthogonal function to extract the leading climate mode on decadal timescale in the tropical Pacific. First, I'm showing the observational results. You can see that on decadal timescales, the leading mode is known as the tropical Pacific decadal variability. It has a spatial pattern that is similar to El Nino or La Nina events. However, if we look at the time series of this variability, it fluctuates between warm and cold phases on decadal timescales rather than year-to-year variations. We also look into the subsurface ocean temperature structure associated with this variability. We find that during a positive phase of TPDV, when the tropical Pacific is warmer, the thermocline deepens in the east but becomes shallower in the west. Next, I'm showing the same analysis based on the ocean initial condition data we provide for the CESM hindcasts, because we do not have very resolved observations for the subsurface conditions. In the past, we have to rely on model simulations to generate those initial condition data. They are generated by running the ocean sea ice simulations forced with the observed atmospheric and surface fluxes and forces. We find that this ocean simulation can very well reproduce the observed features associated with TPDV, this decadal mode. Next, I'm repeating this analysis by looking into the decadal hindcasts, DPLE and DPLE without volcanic forcing. We looked into the spatial pattern, but also temporal correlation scale. We find that the DPLE no-volc shows a pretty high scale in predicting the temporal evolution of TPDV. The correlation is about 0.57, while the correlation scale in the hindcasts with the volcanic forcing is lower. we take a close look at the time series, we find that in observation, around the period with strong volcanic eruptions, the tropical Pacific shows decadal warming signal, while the hindcasts with the volcanic forcing shows cooling response. However, when we do not have this volcanic forcing information, the hindcasts agree better with the observations. We will explore the details about how volcanic forcing degrades prediction scale in a later slide. Then in contrast, the correlation scale in the uninitialized simulations do not show any scale for predicting the observed tropical Pacific decadal mode in the past. This means without the ocean initialization information, we cannot make a scale prediction for the tropical Pacific on decadal timescales. So first, I will answer how does volcanic forcing degrade the tropical Pacific prediction scale on decadal timescales. Here I'm showing how the large volcanic eruptions affect climate. Large volcanic eruptions can release sulfur gases into the stratosphere, where they are converted into the sulfur aerosols, and they can stay in the atmosphere for a relatively longer time, while other materials like water vapor or ashes could be rained out very fast. Those aerosol forcings can modulate the radiative processes, but also trigger a series of dynamical effects in the climate system. It has been very challenging to isolate the climate impacts induced by the volcanic forcing because of the short observational record. And we do not have the direct observations for the aerosol forcing induced by volcanic eruptions before the satellite era. Paleoclimate reconstructions and model simulations have been widely used to deduce the statistically robust response to volcanic eruptions. However, there are still many issues. For example, the disagreements among the paleo reconstructions and also deficiencies in the climate models. It remains unclear how does the volcanic aerosol forcing influence decadal climate and also influence its predictability. Here, we can address this question by comparing the observations in the past and the simulations we conducted for the past. As I have shown that the volcanic forcing degrades the correlation in the tropical Pacific, and I'm showing the results for the forecast year 1 to 10 average. But here we also look into if this degradation is robust across other time scales. And the answer is yes, the scale degradation made by volcanic forcing is robust across multi-year to decadal timescales by comparing the DPLE no-vol, which has a higher correlation scale, which is much higher than the original DPLE. To understand why that, we look into the time series of the volcanic aerosol forcing on the top, but also the Central Eastern Pacific, Tropical Pacific SST anomalies averaged across the box. I'm showing the time series based on observations in black and the ensemble mean forecasts or hindcasts in DPLE showing blue and DPLE no-vol showing yellow. The significant difference between these two data sets are denoted by these gray bars. You can see the significant differences tend to occur when the hindcasts overlap with those large volcanic eruptions. Then we zoom into the 3 period, we find that In observations, this period show warming in the tropical Pacific on multi-year to decadal timescales. When we include the volcanic forcing, there is a cooling response, making the system deviate more from the observations and therefore degrade the correlation scale. However, when we take out the volcanic information, the model can have a better agreement with the observations. This suggests that in observations, this tropical Pacific system is not that sensitive to volcanic forcing. Most of the variability is internally generated due to the interaction between ocean and atmosphere. When the model can have the initial oceanic condition data, they can predict about 30% of the observed variability. Next, we zoom into the period when we have the large volcanic eruptions. Here I'm showing the 5-year average around those 3 large eruptions for the global surface air temperature. As we have found in observations, the tropical Pacific show multi-year warming anomaly, which is well captured by the hindcasts without volcanic forcing. While the volcanic forcing can cause multi-year cooling in the DPLE system, which degrades the prediction for the observations. We then go one step further to look into how does the volcanic forcing cause multi-year cooling response in the tropical Pacific. Therefore, we look into the monthly time series of the tropical Pacific SST anomalies for the Central and Eastern Pacific. I'm showing the case for the Pinatubo eruption starting in 1991. The time series here is in black. The black one shows the observations. On monthly time series, it is influenced by El Nino and La Nina events. And then I also show the difference between DPLE and DPLE no-volc. That is the anomaly generated by volcanic forcing. I'm including the forecast initialized at 10 different initial states around the large volcanic eruptions. The difference between DPLE and DPLE no-volc is 0 at the very beginning because they are using the same ocean initial conditions. But their difference starts to grow when the volcanic eruptions start to happen. There are 3 stages of anomalies in response to the volcanic eruption. The first stage of about 6 months cooling response, followed by a 1 year long week warming response, and then a 2-year cooling response. The third stage of 2-year cooling response is important for forming a multi-year to decadal cooling response in the tropical Pacific. Traditionally, we can use a mixed layer ocean heat budget analysis to understand how this forcing induce the cooling response or warming response in the ocean system. And I will just show the main results. We find that volcanic forcing induced the initial cooling response by reduce the shortwave fluxes received by the surface. While the second phase of warming is more dynamically driven, is associated with the ocean temperature advection processes. This indicates that it is related to the development of El Nino. However, this El Nino-driven warming is still damped by the shortwave reduction caused by the volcanic eruption. Also, the third phase of La Nina, third phase of the cooling response is also dynamically driven associated with the La Nina. events. And interestingly, now the shortwave still plays as an like cooling effect, while during a traditional La Nina event, the shortwave is usually a damping effect for La Nina. This is still showing there is a volcanic forcing driven shortwave reduction even in the third phase of temperature change. Therefore, in summary, we find that volcanic forcing decreases the tropical Pacific decadal prediction scale. This is because the model tends to be too sensitive to the volcanic forcing and generate multi-year to decadal tropical Pacific SSD cooling, while in observations, these eruptions coincided with tropical Pacific warming, which is likely driven by internal climate variability. And in the second part, I will look into what are the internal oceanic processes drive the high prediction scale in the no-volc system. Our results suggest that we need to carefully consider the model fidelity when we attribute any climate impacts to the volcanic eruptions. I've also been involved in a study looking into the volcanic impact on decadal prediction using other state-of-the-art numerical models. And we find similar results that including the volcanic forcing in those systems can degrade the prediction scale. Then we'd like to address the second question: what oceanic processes control the high prediction scale in the hindcast system without volcanic forcing? There are many mechanisms proposed for the origins and oceanic processes affect tropical Pacific decadal variability. And Yuko and her former student also invested this question in like several years ago, and they are also investigating this question by making use of the paleoclimate reconstructions and simulations. It has been argued that this decadal mode could be a residual of random year-to-year variability associated with El Nino or La Nina events. But other studies argue that they could be originated from the stochastic forcing in the extratropical Pacific. Both of these origins are noise-driven. They are not predictable on decadal timescales. However, those processes may initiate some slow oceanic processes and may provide a predictability for TPDV. So here I'm listing the leading mechanisms proposed for TPDV. In our study, we're focusing on understanding which of these oceanic mechanisms provide a source of predictability for TPDV. We analyzed observations, ocean simulations, and hindcasts. We find that the off-equatorial oceanic Rossby waves is the main driver and precursor for TPDV, while the speed of subtropical sail in the tropical Pacific can play as a positive feedback for TPDV once a positive or negative phase is triggered, but they are not the initial driver or precursor. We also look into the spiciness advection, which tends to be out of phase of TPDV and damp TPDV on decadal timescales. In my talk, I will focus on explaining the Rossby wave reflection mechanism. Many recent studies also suggest that other ocean basins can influence tropical Pacific decadal climate. Therefore, we wonder if the influence from other ocean basins can also influence the prediction for the tropical Pacific. We are going to explore this question by conducting regional initialization experiments. I will also introduce this part. This is a very busy plot. The key information is we looked into how does the slow oceanic wave propagation processes influence the tropical Pacific sea surface temperature. And we find that they play as a delayed feedback, as that for the interannual timescales where the Rossby wave reflection can serve as a delayed oceanic feedback for aerosol transitions. But here we are looking at a longer timescale, and those Rossby waves are more far away from the equator. And we are looking into the decadal component by doing a 10-year rounding mean filter. So we are looking to the cumulative effects of those oceanic wave propagations. To well capture the oceanic Rossby wave propagations, we are looking to the isopycnal variability. We are looking to the isopycnal depth, where the density of the ocean seawater equals to 25.5 kilogram per cubic meter. This variability is shown in the color shading. I will try to walk you through this plot. When we have a tropical Pacific decadal warming in the equatorial Pacific, shown by the red contours, this is the longitude time map for the equatorial Pacific. You can see that the equatorial Pacific is experiencing cooling and warming period on decadal timescales. The warming phase of the TPDV, we will have next positive wind stress curl north of the equator, which is indicated by the black contours in this map. Similarly, it will generate negative wind stress curl in the southern part, which I didn't show here. Those wind response can generate upwelling of equatorial Rossby waves that propagate westward. Upon the arriving at the western boundary, they can propagate equatorward and then reflect into the upwelling Kelvin waves. Those upwelling Kelvin waves can show the thermocline and weaken the initial SST warming and trigger the phase transition of this decadal mode. Here we have a loop from the initial SST variability, which influence wind and associated oceanic subsurface temperature response. And then this plays as a delayed feedback to influence the initial SST warming. We could also conduct lead lag correlations to better quantify this relationship. This main conclusion is the subsurface isopycnal variability can precede the tropical Pacific decadal SST variability by over 7 years in advance. Therefore, those isopycnal depth variability and associated oceanic wave processes may play as a precursor and provide source of predictability for TPDV. To confirm this, we further look into the correlation analysis based on the hindcasts in the DPLE no-volc. Here again, we are correlate the predicted SST sea surface temperature index in this box averaged across forecast year 1 to 10. First, we are looking into the concurrent correlations. You can see that in the forecast, now we have this decadal mode being set up in both sea surface temperature and also thermocline. Also the isopycnal depth spatial patterns, we have like thermocline or isopycnal depth deepening in the east, but shallower in the west. Then we calculate the correlation of this index with the initial conditions precede these 10-year predictions, we can find out what are the precursors for the prediction. We find that the prediction for TPDV is not correlated with the initial SST information in the tropical Pacific. However, it shows significant correlations with the subsurface temperature below 100 meters. Even clearly, we find that the isopycnal variability in the initial condition in both equatorial and off-equatorial Pacific is important for the prediction. This confirms that the initial ocean memory stored in the subsurface isopycnal depth variability provides the predictability for TPDV at a 10-year lead times. Although we do not identify significant correlations in the tropical Pacific, but we saw some negative and positive correlations in other ocean basins. We wonder that if those correlations indicate causality, and if those ocean basins, the information in other ocean basins can provide a source of predictability for tropical Pacific. Therefore, we conduct regional initialization experiments. Here we focus on a case study during the period of 1999 to 2018. The top map is showing the decadal sea surface temperature anomaly during this period. We have the tropical Pacific cooling in this period, and this is a period known as global warming hiatus, where we have a slowdown in the global warming driven by this tropical Pacific cold phases. This 10-year cooling is well predicted by the DPLE no-volcano with global initialization of the ocean. And the third map is showing the corresponding initial condition for these hindcasts. We'd like to know which part of the ocean initialization is more important. So we first conduct a control experiment called climatology initialization. In this experiment, we're not given any observed conditions on that day for the model. Then we conduct the tropical Pacific initialization experiments. We are initializing the ocean with full depth ocean temperature and salinity anomalies on November 1st of 1998, but plus on the global climatology everywhere. The model only has the information for tropical Pacific in this experiment. Similarly, we conduct North Atlantic and Southern Hemisphere ocean initialization experiments. And those experiments are also run under the radiative forcings during the 10-year period. We have 10 ensemble members for each experiment. Then we remove the control simulation from the other 3 sets to get the forecast hindcast anomalies. I will show you the result. We find that the decadal cooling in the original DPLE experiment during this time period is well reproduced when we only give the model the tropical Pacific initial conditions. While the North Atlantic initialization experiment is critical to reproduce the North Atlantic decadal warming during this period, but it doesn't further trigger any further response in the tropical Pacific. In contrast, the initialization of the Southern Hemisphere oceans trigger the warming response in the tropical Pacific. But note that this is a prediction error because this warming in the Southern Hemisphere is in an opposite phase with the observed values. This means that the prediction error in Southern Hemisphere may also degrade the prediction scale for the tropical Pacific. In summary, for the second part, we find that the high predictability for tropical Pacific decadal variability in the no-volc system is largely arising from the decadal isopycnal depth variability and associated oceanic Rossby wave propagations. I didn't discuss in this talk, but we find that the initial predictability is further amplified by the tropical ocean atmosphere coupling and also variations in the subtropical ocean sails throughout the decadal hindcasts. We also use the regional initialization experiments to effectively isolate the impact of different ocean basins on tropical Pacific decadal prediction. We highlight that most of the predictability is provided within the tropical Pacific. I'd like to briefly discuss what are the remaining challenges and potential solutions for improving the tropical Pacific decadal prediction. First of all, we need to reduce the uncertainties in observations and reanalysis data sets, because the instrumental records are very short and they are even not very insufficient for studying the decadal climate variability. Therefore, it is important to improve the current observing systems for the L, sea, and upper ocean processes. I haven't discussed, but we find that there are even discrepancies among the current observational or reanalysis data set for the subsurface ocean conditions. We could also incorporate paleoclimate records to achieve the statistically robust results and constraint models. The community has actually looked into that. Here is a figure from a review paper by Antonietta Capotondi, and the main conclusion is the current short instrumental record tends to underestimate the range of the tropical Pacific decadal variability compared to the model simulations and also paleo proxy or data simulations. On the other hand, we also need to reduce our model biases in simulating the climate for both climatology variability and forced response to any external forcings, as well as the interbasin interactions. By improving the prediction skill in the tropical Pacific is important for the global climate. We know that this decadal mode can modulate the global surface temperature, global average surface temperature on decadal timescales. We tend to have a slower global warming rate during the negative phase of this decadal mode. Therefore, predicting this mode better can help us better predicting the speed of the global warming. It also influences the interannual variability like ENSO events, and also modulates the global hydroclimate and marine ecosystems on decadal timescales. So when we improve the prediction skill for ocean atmosphere coupled processes in the tropical Pacific, we can also improve the prediction. We may also be able to improve the predictions for many other aspects of the Earth system. And we have been developing research to see if those ocean predictability can provide a further source for the associated impacts. That's all for my talk. And as Yuko mentioned, I have been developing a new group at UT Dallas, and I'm happy to develop any collaboration with people at UTIG as well in the future. That's all. Thank you so much.
Thank you for the great presentation, Xian. So we'll take question from student first.
That working? Great. So when you say that you apply the volcanic forcing, like what parameters get forced for how long, and how are they determined when they get plugged into the model?
So for climate simulations, we are just use the aerosol forcing induced by volcanic eruptions and use it as a forcing fire for the input provided for the model. It is kind of like not very well resolved because we do not have globally resolved observations for those aerosol forcings. But the forcing fire is as a function of latitude and also has a temporal evolution with it on monthly timescales. So I'm not sure what are the parameters you are asking about.
Well, I guess that sort of answers it. You know, there's a spatial component to it, right?
Yes, yeah, thank you.
Nice talk. Thank you. So in the complicated figure that you had that you walked us through, I think it was a Hofmahler, where you had the Rossby waves bouncing off on Decadal. Yes. So the Rossby and Kelvin waves are much faster than the 10-year. They're happening throughout the year, throughout the months.
Right.
So is there a particular season or interannual event where those start to accumulate to show up in that 10-year running mean that you have there?
If we look into one time wave propagation for the Rossby wave at the latitude band of 10 to 15 degree north, the travel time from Central Pacific to the western boundary is only about 2 to 3 years. But here we are doing a 10-year running mean filter to it. We are looking to the cumulative effects of many times of propagations and looking to how they influence the decadal climate.
Right. So is there a particular season that matters more to accumulate the decadal signal, like spring, fall, or is it like during El Niños or during La Niñas to give you the decadal signal?
I haven't looked into the seasonality. It's a good question. I haven't looked into that. Here, I'm just first to take the annual mean data and then take the 10-year only mean data. If we look into the seasonal or annual mean field, we will see most of the variability is dominated by aerosol, but it could be interesting to further look into if the decadal mode has a seasonal variability. Thank you.
Any other question from Damian?
Oh, no.
So I'm curious, going back to the conclusions from your first half of your talk, one of the things that you kind of arrived at this idea that the models are overly sensitive to the volcanic forcing.
Yes.
I'm wondering, does this point in a direction where the models themselves have something that's not right in the physics that needs to be revised or recalibrated? And how big of an issue is that, do you think?
There could be multiple causes. First of all, there is uncertainties in estimating the aerosol forcing induced by volcanic eruptions, as I have said. We do not have a lot of observations for that. Second, the atmosphere model used in this Earth system model does not have a well-resolved stratosphere, and most of the aerosol forcing actually stored in the stratosphere. That could be another reason. And third reason is there is biases in the tropical ocean atmosphere interactions in this model. The model has too strong positive ocean atmosphere feedbacks and makes it too sensitive to any external forcings. Thank you.
Thanks, Xian. That was a really great talk and helped me understand part of our proposal as well. I kind of following on Damien's question. So have these simulations been run in the high top model and the Wacom model? And also, is there a chemistry component too that can help with the volcanic forcing? I'm not sure if chemistry is turned on for aerosols in this model setup. Yeah.
In the CSM1 seasonal or decadal hindcasts, or even the CSM2, they both use CAM5 or CAM6, which doesn't have a very well-resolved stratosphere. But I know other groups at NCAR, they have conducted Vulcan, the high top atmosphere model-based simulations to look into like more volcanic forcing driven research. They focus on short time scales like subseasonal or seasonal time scales. But for the long-term decadal predictions, those models haven't been incorporated yet.
Do you see value in doing that at
Yes.
all, or do you feel like it's beyond that issue?
I think it could be very useful because there is a recent study based on Vulcan find that for the recent eruption, which is not included here, the Tonga eruption, they looked into the influence of Tonga. Tonga is special because it doesn't release a lot of sulfur gases. It releases a lot of tons of water vapor. So they look into how the water vapor forcing influence the response in both stratosphere and global climate. I think they didn't see a very strong response over the tropical Pacific based on their volcanic experiments for the Tonga case.
Thank you.
Thank you, Xian. I have a following up question about the vacuum. But they're good at the stratosphere processes, but for the troposphere, like ENSO, I think I don't know how the ENSO performance on this vacuum. Maybe they're bad at it since they don't have many layers. So there might be like is it possible we could use like Wycomb's result from stratosphere and and use CAMS, look at the troposphere and so process to improve the scales or something?
Yes, I'm not familiar with how the coupled model using vacuum in simulating ENSO. I presume it could be very similar because most of the ENSO simulation depends on the lower part of the atmosphere and ocean. But it could be useful if we can combine the information from vacuum and use that as an input for the traditional CAM-based experiments.
If the model seems overly sensitive to the volcanic forcing, which is an aerosol forcing, and the aerosols are poorly constrained, and other people look at aerosols from different sources, are other people's aerosol sources potentially at risk of, having the same outsized model impact?
I got the similar question before. I'm not familiar with that. So I feel like the community had always had a hard question when they try to use the model simulations to explain observations, because we only have one time realization in the short observational record. When we try to use model simulations to explain what's happening in observations, it's always hard. We don't know if the disagreement between observation and model is coming from uncertainties in one realization due to internal variability or due to the model biases. It's an open question to answer. Thank you.
Any other question? And do we have any question online? Okay. If we have no more question, and let's thank Xian again for the great presentation.
Thank you.
And the student and the postdoc lunch meeting will be happening on the second floor, of the conference room, the UTIG.